All right, in this video, so I'm going to do just a brief review over naming and bonding. So hopefully this kind of helps you out a little bit. So we're just going to start here on the periodic table. So if you're watching this with me, you will need a periodic table. You can also use this to help you with your homework as well. And I also have a list of the polyatomic ions, but I'm going to do those last. I'm going to just start off with the simple stuff first. So we're just going to go over some bonding and naming. So first thing we need to look at is our periodic table on here. So bonding is based on charge. And so if you don't know how to find charge on a periodic table, you're going to get lost pretty quick. Okay, so we're going to kind of go over that real quick and kind of see how to find the charge of our elements on the periodic table. So first thing is called the octet rule. So we kind of talked about this, is elements want to have 8 valence electrons. So that's the perfect number. Okay, so we're going to zoom in on some of these. Okay, so we kind of taught y'all a trick last unit on how to find valence electrons in the periodic table. It was these numbers right here. So you see 8A, 7A, 6A, and so forth. Okay, so that is our number of valence electrons. Okay, so the perfect number is 8. So this whole right side over here, helium, neon, argon, krypton, xenon, radon, they have 8. So they don't really need to bond with anybody to get extra electrons. Okay, so they're cool with being on their own. Okay, so they have over here, they have a charge of 0. Okay, so they don't need any more. Now, if you look at this next row, fluorine, chlorine, bromine, iodine, okay, they have 7 valence electrons. So remember, the perfect number is 8. So it's basically saying that we're missing one. So we just need one more. So what they're going to do is they're going to gain an electron from somebody, which gives them a -1 charge. Okay, then we go over to 6A. So I'm basically missing 2, so it's going to be a -2 charge. 5, I'm missing 3, so -3. Okay, 4, this is where it can go plus or -4. Okay, so carbon, silicons, those can go either way. So it can try to either give up 4 or it can try to gain 4. Usually when we deal with carbon, it's usually going to be a negative for most of our cases because it's bonded with something positive. Okay, so then we move over here to 3A. So what this is going to be a +3. Okay, so the odds of boron finding 5 electrons for someone to give to it is pretty slim. Okay, so it's got better chances of bonding with someone who has 5, so it can give up its 3. Then we're going to come over here. So we got 2A, 1A. Okay, so beryllium, magnesium, they have 2 valence electrons. They're not going to find 6, so this is basically saying, hey, I have an extra 2. Or it also says, since I'm giving up 2 electrons, that's why I have a +2 charge. Since I lost electrons, I have more protons now. But I just look at it like, hey, I've got an extra 2 that I can bond with someone who needs 2. Then our left column is going to be +1. Okay, so that is how you kind of determine your charges. So if you just want to memorize it straight up on where to put those charges, you can do that. Okay, so but if you don't know how to find those or how to repeat that, you're going to get in trouble pretty quick. Okay, then this middle section right here, this whole middle section, basically starting on the D section all the way to the staircase, is going to be called transition metals. So all starting right here and then going over to the staircase is going to be our transition metals. Okay, bear with me, my pen's not working very well. So these are our transition metals. What that means is that their charges can vary. Okay, so it can change depending on who it's bonded with. So that's when we use Roman numerals to dictate the name of that. So we'll get to that after we start nice and simple. Okay, so let's do some examples. So I'm going to start off nice and simple. We're going to just do monatomic ions or monatomic ions. So remember, monatomic means singular or one. Okay, so examples of that would be something like Na with a plus charge is bonded with Cl with a minus charge. Okay, so this is monatomic ions. I have 1 sodium and I have 1 chlorine. Okay, so Na is going to be monatomic and Cl is going to be monatomic. Okay, polyatomic means many. So those you'll see in this list down here. You can see multiple elements in one combination. That's a polyatomic. So for now, we're just going to stick with monatomic. Okay, so the whole purpose of bonding is to achieve a charge of 0 when they bond. Okay, so they want to be perfectly balanced. So if I have a plus, which is basically the same thing as +1, and a minus, which is the same thing as saying -1, and I want to bond these two together, since they're already balanced, the +1 and a -1, that's what you want to achieve, is you want to have the same positive number as you do the negative number. If I have a +1, I need a -1 to be balanced. So if I were to bring these together, it would become NaCl. Okay, so nice and easy on bonding. Now, as for naming, so cations, we never change the name. Okay, so Na is just sodium. So your cation, so just remember that your cation is the positively charged ion. It's just going to be sodium. Now our anion, which is the negative charged one, when it's bonded, it's going to change its name and it's going to end in "ide." So instead of chlorine, this becomes chloride. Okay, super simple. That's it. So just sodium chloride. So I'm going to erase these as we go. If you need to rewind anytime, you can do that as well. Okay, I just don't want to have too many sheets on here. Okay, then I'm going to have something like Ca plus 2, O minus 2. Okay, so I have calcium and oxygen. So I see that there's a +2 and a -2. So these two are already balanced, okay? So I don't need any more of either one. So if you brought these together, this would just be CaO. Now, we also taught you something called the crisscross method. So the crisscross method helps us in our balancing. So if I did the same thing, so let me erase this real quick. So Ca plus 2, O minus 2. The crisscross method is where you take the number, not the charge. So I would take this 2, bring it down here, and take this 2, bring it down here. And then your answer would be Ca2O2. So this is where you have to be careful. There's nothing wrong with doing the crisscross method. It's just like in math, if it can be reduced, it needs to be reduced. So I don't need 2 calciums and 2 oxygens to be bonded. I only need 1 of each. So these 2's, so common factor of 2, both these can be divided by 2. So correct answer would just be CaO. So just remember, you can do crisscross method, but if it can be reduced, it needs to be reduced. So the name for this, so remember we don't change the cation, so that's just calcium. Oxygen, now that's our anion, it's going to change its name, so we're going to put "ide" on the end of it. So now this becomes oxide. So calcium oxide. So when we do the IDE, this is for monatomic anions. Okay, so we use IDE for monatomic anions. Okay, so if it's just one anion, that's all you gotta do is just put an IDE on the end of it. Okay, so now let's try another one. So let's say we have Al plus 3, so aluminum, and we have oxygen with a -2 charge. Okay, so I can tell right now that these are not balanced. So you can do the crisscross method here. So you can take this 2 down here and take this 3 here. So basically that states that I need 2 aluminums and 3 oxygens. So that is the crisscross method. So I'm done. So the way you could check yourself on that is to make sure your charges are equal. Is if I have 2 aluminums and each one is charged +3, that means my total charge for aluminum would be +6. Now if I have 3 oxygens and each one has a charge of -2, 3 times -2 would be a -6. So those would perfectly balance each other out. Okay, so that is a way to check yourself. If those numbers don't match, then your formula is not balanced. So let's do our name for this one. So aluminums are cations, so we're going to leave it as aluminum. Oxygen, so that's our anion, so it's going to change to oxide. So aluminum oxide. Okay, so let's do some more. Now let's go backwards a little bit. So I'm going to do Na2O. Okay, so here you can do that. So you can do a reverse crisscross method. You just have to be careful and check yourself with the periodic table. Because remember, these can be reduced, so it may not always work. So if we did the reverse crisscross method, this 2 would come up here. And then there's an imaginary 1 right here on this oxygen since we only have 1. So I would carry that 1 up here. So that means Na would have a +1 charge, and oxygen would have a -2 charge. So we're going to go to our periodic table and make sure we're correct. So oxygen is right here, has a -2, so that's correct. Na is over here, that has a +1, so that's correct. So that's easy. So that one, that reverse crisscross method worked, and we're done. And if we wanted to know the name of that, that would just be sodium oxide. Okay, so that was the reverse crisscross method going backwards. So let's try another one. Let's do MgO. So magnesium oxide. So if we did the reverse crisscross method, so this is where you got to watch out. I have 1 magnesium and I have 1 oxygen. So if I did reverse crisscross, this 1 would go up here and this 1 would go up here. So basically that's stating that Mg +1 and oxygen -1. Okay, so let's check our periodic table. Okay, oxygen should have a -2. So we already know that that's not correct. Okay, so this is where you got to be careful. Oxygen has to be a -2. So O -2. So that reverse crisscross method does not work here. Okay, and then you would look on your periodic table, and Mg is right here, and that would be a +2. Okay, so the reason why is because let's say we started back with, say we started with this. Whoa, sorry, went to the top of the screen, shouldn't have gone there. Okay, let me clear up some room a little bit. Okay, so let's say we start with Mg +2, and we have O -2. Now, if you did your crisscross method going down, you would bring this 2 here, bring this 2 here, and you would get Mg2O, 2. Well, that can be reduced. So the correct form would be MgO. So that's where the reverse crisscross can get tricky, is whenever something is reduced. So the way I do it is, so let's start back on that one again. Let's just do MgO. So for these, you can usually look on the periodic table. If you can find your charges in the periodic table, it makes it pretty simple. So oxygen is always going to be a -2. And then Mg, if you look at Mg is going to be a +2. I just found those by looking off the periodic table. So that helps out a lot. So let's do another one. I have Be3N2. So I can do reverse crisscross. We'll try it and see if it works. So this 3 goes up here to the N, and this 2 goes up here. So that's basically stating that Be has a +2 charge, and then N has a -3 charge. So let's look at our periodic table and see what we got. So Be is going to be over here. That has a +2 charge. Okay, N should have been a -3 over here. So N is right here, so that's -3. So that's done. Okay, so if I wanted to know the name of that, that would just be beryllium nitride. Okay, so now you're kind of getting the gist of that. So sometimes the reverse crisscross method works, but you just really need to make sure to pay attention to your periodic table to double check yourself. Okay, so again, I cannot stress it enough. If you don't know how to find charges on a periodic table, that will prove troublesome really quick, and we will be using that for the rest of the year pretty much. So I would just get in the habit. If you have to just memorize it, that's fine. So let's just do one by name. So say I give you aluminum chloride. Okay, so I'm going to find out my ions first. So aluminum is right here, has a +3 charge. And then chlorine. Okay, let me clear some of this up. Chlorine is right here, and that has a -1 charge. So you can do your crisscross method here. So I'd take that 1, bring it down here, and take this 3 over here, and I have Al Cl3. That's it. That's all I had to do to balance that. Okay, so let's do another one. Let's do strontium carbide. Okay, so strontium. Let me clear these up. Strontium's right here. So Sr has a +2 charge. So I don't know why my name kind of erased there. So that would be strontium carbide. So this would be Sr +2. Carbide is just carbon, and that has a C with a -4. So here's where you can do the crisscross method if you want to. You can bring this 4 down here, and you can bring this 2 down here. So that'd be Sr4C2. Okay, both are divisible by 2, so this needs to be reduced. So that would be Sr2C. Okay, so the way I look at this is if carbon has a -4 charge and strontium has a +2 charge, ultimately I need to get strontium to +4 to balance out. Okay, I don't want any more carbons if I don't have to. Okay, so I know if I did 2 times +2, that would give me +4. So which would give me Sr2C. Okay, so you don't necessarily have to move the big one if you don't, like carbon is my big one that's got the -4. I don't want to make more if I don't have to. Okay, so that was kind of just the basic. When we know the charges of everything, we're doing just monatomic. Okay, we haven't moved into transition metals yet. So now we're going to actually move into transition metals. Okay, so let me clear some of this up on the periodic table. Okay, so our transition metals, remember, that starts at our D group. So it basically starts all through here and then travels right to the staircase. Okay, so we do have some exceptions though. So let me clear these off a little bit. I'm going to zoom in. We're going to do a different color here so I can leave these here. So silver is always going to be a +1. Zinc is always going to be a +2. And then aluminum is going to be a +3. Okay, so those are the exceptions there. Those will never change. So when we get into using those, if they never change a charge, we don't need a Roman numeral to tell us what it is. Okay, so we also have a couple others. We have tin and PB. Tin and PB, which is lead. So they're either going to be +2 or +4, and lead's going to be +2 or +4. So those are our only options for those. We still need Roman numerals for them, but those are the only 2 options they can be. These other ones can be anything. So what that means is we have to use Roman numerals to tell us what charge they are. So if you need a recap on Roman numerals, 1 is just I, 2 would be II, 3 is just III, 4 is where you can kind of get a little tricky. That is going to be IV. 5 is just going to be V by itself. 6 is going to be VI. And then lastly, the last one you're going to use is 7, which was VII. Okay, so those are your possibilities. So it just depends on who it's bonded with, which will determine its charge. So let's start off with an easy one. So let's just do, let me change my color up. Fe with a 3+, and chlorine with a -1. So keeping it nice and simple. So I can tell that they're not balanced, so I'm going to do my crisscross method, so just like we've been doing before. So I'm going to bring that 1 over here, bring that 3 over here. So my correct formula would be FeCl3. Okay, so it's nice and balanced, that's it. So now the trick is when it comes to naming, now we have to put the Roman numeral in the name to tell us the charge of iron, because iron could honestly be anything. So we're going to write out iron. So remember, that doesn't change. Our cation's name never changes. Now, we have to put a Roman numeral for a transition metal. Okay, if it's, I'm going to use a random color here. So let's do orange. If it falls in group 1 or 2, okay, or anything right, well, anions will never need a Roman numeral. Okay, their charges are not going to change. But also, if it falls in group 1 or 2, that's not a transition metal. We do not need a Roman numeral for those because it's always going to either be +1 or +2. Never going to change. As soon as you get to that D group, that is when the charges will change depending on who it's bonded with. So that's why we have to put a Roman numeral on it to tell us what the charge is for that specific iron. So in this specific case, iron has a charge of +3. So you're going to put I. Okay, so iron 3, so that tells me the charge of iron, not how many I have. Okay, and then you're still going to do the same thing. So chlorine is going to now be chloride. So that is iron 3 chloride. Okay, so let's do another example of it. Okay, so let's do Fe +2 and Cl -1. So pretty much same thing. Okay, so I'm going to do my crisscross method. So 2 would go down to the chlorine, 1 would go to the iron. So this would be FeCl2. Now if I'm going to do my name, it's still going to be iron. Now it's a +2 charge. So this is going to be iron 2 chloride. Okay, so again, that Roman numeral is to tell us the charge of the cation, not how many. Okay, so let's do another example. So I have Pb with a +4, and I have phosphorus with a -3. Okay, so I can go ahead and say that it is not balanced. So I'm going to do my crisscross method here. So I'm going to bring that 3 over here, bring that 4 over here. So my balance formula would be Pb3, P4. Okay, so again, if you want to check yourself on charge, you can. 3 times +4 would give me +12 for lead. 4 times -3 would give me -12 for phosphorus. So this is perfectly balanced out. So again, if you want to check yourself that way, you can. So we're done balancing, so that's our formula. Now our name, so Pb is lead. So now we're going to tell what the charge is. So this lead has a charge of 4. So this is going to be IV. So lead 4, and then phosphorus now becomes phosphide. Okay, let's do another one. So again, you can rewind anytime you want on this if you need to. If this is stuff that you already kind of know, you can fast forward to we're about to do polyatomics. I know that kind of gets a little more confusing, but hopefully this is helping with the transition metals. So now we're going to do zinc with a +2 charge, and we're going to do iodine with a -1. Okay, so it's not balanced, so I can do my crisscross method. So that would just be ZnI2. So now it's balanced. Now we're going to do our name, zinc. This is where you have to be careful. Zinc is one of these 3. So these 3 right here, they never change. So zinc is always going to be a +2. If the charge never changes, you don't have to tell me the Roman numeral. We already know what it's going to be. So it would just be zinc iodide. So even though zinc falls under that transition metal category, those are those 3 exceptions that they do not need a Roman numeral. Okay, we only need Roman numerals for the elements that can change their charge. Okay, so let's do another one. Let's see. Now let's go backwards. Let's do Ni2C. Okay, so you can do your reverse crisscross method here if you want to try. So I would bring this 2 up here, and I would bring this 1 up here, and I would have to see if it's correct. So I would basically saying C with a -2, and then nickel with a +1. Now nickel's right here. So honestly, nickel could be anything. So I'm not going to check the cation. What I'm going to do is I'm going to check my anions. Your anions are never going to change. So that's something you need to really focus on. So usually the best thing for doing these when you're going backwards is to start with the anion first. If we look at carbon, let me clear up these orange lines real quick. Carbon's right here. Okay, so it has a charge of -4. So we know this is not correct. This is a reduced formula. So the way I do this is, let me write this again. Ni2C. So the way I do is I always start with the anion first because those aren't going to change. So carbon's right here, so it has a charge of -4. So that's stuck. Can't do anything with that. Now, I have 2 nickels. Okay, so and I need to get to a +4. So what I'm going to do is +4 divided by how many nickels I have, which is 2. So that means I'm going to have 2 of them. Okay, where the charge of each one is going to be a +2. Okay, so that means this nickel is going to have a +2 charge. Okay, if you want to check your answers, you can check your charge. 2 times +2 gives me +4. I only have 1 carbon. 1 times a -4 is a -4, so that's perfectly balanced. Okay, so now we're going to do our name. So this would just be nickel. And nickel is not one of my 3 exceptions, so we do need a Roman numeral. Okay, and it has a charge of +2, so this can be nickel 2. Carbon now becomes carbide. Okay. Hopefully this is starting to make a little more sense. Okay, let's do another one. We have Mn2S7. Okay, so we're going to see where is sulfur. Sulfur is right here. And then Mn is going to be right here. Okay, so here you can try to do your reverse crisscross method if you want. Okay, sometimes it works, sometimes it doesn't necessarily work because of if it's reduced, it's not going to help much. So I'm going to bring this 2 up here, and I'm going to bring this 7 up here. So that's saying S has a charge of -2, so let's check. S over here has a -2 charge, so that's correct. So that's when the reverse crisscross method works, is if your anion matches up, then it works. So that means manganese here has to have a +7. Okay, so if you did not do the crisscross method, so Mn2S7. Okay, I'm going to start with my anion, which is sulfur. I know sulfur has to have a charge of -2. Has to, because that's the way it is in the periodic table. So 7 times -2 is -14. Okay, so my manganese has to reach +14. I only have 2 of them. So 14 divided by 2 is going to give me 7. Okay, so that means each manganese, I only have 2 of them, each one's going to have a charge of +7. Okay, so there's 2 ways to do that, so whichever way works for you. So that's how we split it up. So now we're going to do our name. So now that we know the charge of manganese, so you're going to do manganese. And it has a charge of 7, so this is going to be VII. And then sulfur has now become sulfide. Okay. Let's do another one. So now I'm going to give you the name. So let's try silver phosphide. Okay, I always start with the anion because, again, they don't change. So phosphorus is number 15, so phosphorus has a charge of -3. And then silver, okay, right here, that's one of our exceptions. Okay, Ag +1. You can also notice is they did not have a Roman numeral in that name. I did not give you a Roman numeral in that name, so that's telling you that silver is one of those few that does not change. So now I would just balance it. You can do the crisscross method, so bring the 3 down here, the 1 here. So your balance formula would be Ag3P. And that's it. Okay, let's try another one. Let's do mercury 1 oxide. Okay, I'm going to start with oxygen, my anion. So that's going to be O with a -2. Mercury is going to be abbreviated Hg. So if you need help finding that, it's under Hg. Hg, and that Roman numeral 1 told me that I have a charge of +1. So that Roman numeral tells me the charge of mercury. Now I would do my crisscross method. So 2 is going to go to the Hg, so that means I need 2 Hgs. And I only need 1 oxygen. So that's balanced out. So that's it. That's done. Okay. Let's do one more, and then we'll move on to polyatomics. So I'm going to do chromium 3 nitride. Okay, so I'm going to start with nitrogen. My anion, so N is going to be a -3. And this chromium has a charge of +3. So those are balanced out. So that would just simply be Cr(N). That's it. So you do not need to do the crisscross method if they are already balanced. If you have a +3 and a -3, you're done. That's it. Okay, so now let's move on to the fun stuff, which is the polyatomics. Okay, so down here real quick, we're going to talk a little bit about these. These are your polyatomic ions. So again, poly means many. So that means you're dealing with compounds that have multiple elements or atoms in one. Okay, so one thing we got to watch out for is your name changes. Okay, so we're probably going to give you all the 8s, and then we're going to have to ask you to know how to change the name if we take away oxygens or if we gain oxygens. Okay, so the first rule down here. So if we just start with, we'll just do chlorate first. So chlorate is ClO3 with a minus charge. Now, when we go from 8 to ite, okay, so if our name changes from 8 to ite, that suffix changes from 8 to ite, we lost an oxygen. Okay, so now that would become ClO2 with a -1 charge. Okay, so this is chlorate. Okay, once we lose an oxygen, this would be chlorite. Okay, so let's take another example. So phosphate, so PO4 with a 3- charge. So this is phosphate. Now, if we lost an oxygen, so PO3 with a -3 charge, this is now phosphite. Okay, so it did not affect our charge at all. We just lose an oxygen. So if you lose 1 oxygen, it goes from 8 to ite. So it's not a specific number of oxygens, it's just if you lost one, because chlorate has 3 oxygens and phosphate has 4 oxygens. So it's not the number of oxygens that's telling us what 8 actually is. It's just when we change the name, that means we lost an oxygen. Okay, so let me clear some of this up. Now, if we lose 2 oxygens, so now this becomes ClO with a minus charge. So we were at 3, now we lost 2. Okay, it's still going to end in ite because we lost oxygens, but now we're going to add the prefix hypo. Okay, so this now would be hypochlorite. The way I try to remember that is people with low blood sugar, like hypoglycemia. Hypo means low. Okay, so when people go hypoglycemic, okay, they have low blood sugar. Okay, so that means we're getting too low, so we lost 2 oxygens. Okay, so those are if we lost oxygens. Now, if we gained one, so now I have ClO4 with a -1 charge. If I gain an oxygen, it's still going to end in 8. Okay, remember we only change the ite if we lose oxygens. If we gain an oxygen, we're going to add per to the front of it. So now this becomes perchlorate. So you had our original, which is chlorate. We lose 1 oxygen, it becomes chlorite. If we lose 2 oxygens, this becomes hypochlorite. And if we gain an oxygen, okay, we're still going to keep that 8 suffix, but we're going to throw a per on the beginning of it. So this is now perchlorate. Okay, so that was just kind of a little refresher on that. So now we're going to try to do some balancing using those. Okay, so let me zoom in a little bit. So let's start off simple. So I have RB. Oop, that didn't work out. RB with a +1 charge. And I have ClO3 with a -1 charge. Okay, right now I can say that the charges are balanced. Okay, so we don't need to do anything. Okay, what I will say is when we deal with polyatomic ions and you see ClO3, this number right here, do not touch this number ever. Okay, we can't reduce it, can't move it up top for a charge, nothing. It is just stuck with chlorate. So it is just a part of it and you cannot do anything with it. So just be careful with that. Okay, so it's charged, it was balanced. I have a +1, -1, so I don't need any more of either one. So this would just be RbClO3. Okay, so we're going to do our name. So Rb is rubidium. Okay, so this is where you got to be careful is we need to check, is it a transition metal? Okay, if it is a transition metal, we need a Roman numeral in our name. So rubidium is over here. Okay, that is always going to be a +1. That is not a transition metal, so we do not need a Roman numeral. So this would just be rubidium chlorate. Okay. So now let's do another one. Let's do Rb plus with a ClO2. Okay, charges are still balanced, except our name now changed. Okay, so charges are still balanced, so this would be RbClO2. Now we're dealing with rubidium. We lost an oxygen, so now this is chlorite. Okay, if I took away another oxygen, that would be rubidium hypochlorite. If I gain an oxygen on the chlorate, it would be rubidium perchlorate. So that's just something for you to know. Okay, bear with me, I have allergies. So let's move on and do something else. So let's do this. So I have Ca plus 2, and I have NO2 with a -1 charge. Okay, right now I can see that my charges aren't balanced, so you can do the crisscross method. So this 1 would go over here, and this 2 would go over here. So I only need 1 calcium. Now, when you need multiple polyatomic ions, what we're going to do is you're going to put that polyatomic ion, the whole thing, in parentheses. So I'm going to put NO2 in parentheses. I'm not going to touch that 2 on the O at all. I'm just going to leave it alone. Now I needed 2 of those, so I'm going to put it in parentheses, and I'm going to put a 2 outside here. So now I'm done. So when we do the name, calcium, so Ca is calcium. Is calcium a transition metal? It's right here. No, it's not, so we don't need a Roman numeral. And then we look up NO2 on our list. Okay, NO2 is right here, so that's going to be nitrite. So this would just be calcium nitrite. Okay, and that's it. Okay, so let's try. Let's do Ag plus, and then Cr2O7 with a -2. Okay, right now I can tell it's not balanced. You can do the crisscross method. I'd bring the 2 over to Ag. Ag. Okay, I need 2 of them, so Ag2. Okay, I would take that 1 over to that. So that means I don't need any more of the Cr2O7, so I'll just put Cr2O7. So you do not have to put parentheses around it if you don't need more than 1, okay? Because this would just kind of be pointless because we know there's just 1 of them. So you don't need parentheses around that. Okay, so now let's look at our name. So Ag is going to be silver. Is silver a transition metal? Okay, silver is in our transition metals, but it's one of our exceptions, so we do not need the Roman numeral. Okay, it's always going to be +1, so this would be silver. And Cr2O7 is right here, so that would be dichromate. So this is right here is silver dichromate. Okay. So let's clear this up. Now let's change this a little bit. I'm going to use the same dichromate, but now I'm going to do Fe with a +3 charge. So Fe +3 is trying to balance out with this dichromate with a -2. So I can do your crisscross method. So I'd bring the 2 over to the iron. So I need 2 irons. And I would bring the 3 over to the dichromate. So I'm going to put this whole thing in parentheses. So Cr2O7. Okay, and I needed 3 of them. So I'm going to put 3. So I'm done balancing. That's balanced. Now my name would be iron. Iron is right here. Okay, that is a transition metal, so we do need a Roman numeral. So this would be iron 3 dichromate. Okay, that's it. Pretty simple. Okay, let's do some going backwards. So we're coming towards the end of this. So I have LiClO4. Okay, so again, I always start with my anion. I'm going to go ahead and figure out what that is by itself. If I look up ClO4, ClO4 is right here. It's perchlorate. Okay, so I know I'm dealing with ClO4 with a -1 charge. Now this is where you got to be careful. I've seen this mistake before. So LiClO4. What people will do is they take this 4 and they bring it up here and they say lithium has a charge of +4. Okay, so remember that 4 is attached to perchlorate. It doesn't go anywhere. You can't reduce it, can't touch it, can't move it. Okay, so be careful with that. Do not do, so I'm going to put this in red. Do not do this. Okay, so do not touch that 4. Okay, now I'm going to look at lithium. So ClO4 is a -1 charge. I only have 1 of them. I only have 1 lithium. So this formula that we give you is already balanced. So that means it would have to have a charge of +1. So you can also look on your periodic table. Lithium is right here as a charge of +1. So that's it. Okay, so let me clear this up. Let's do our name. This would be lithium. Okay, we already knew lithium was not a transition metal. We just found it as number 3 on the periodic table. So we don't need a Roman numeral. So this would just be lithium perchlorate. Okay, that's it. Okay, now let's do this one. Let's do BaNO3 with a 2. Okay, so this is where I start with the anion. So I would look up NO3 on the list, and that would be NO3 with a -1 charge. I'm going to look up Ba. Ba is number 56 over here. Ba has a charge of +2. Okay, so this is where the reverse crisscross method could work. So you could take this 2 up here and this 1 up here. So it does work, but you just got to be careful. I would check yourself with your list and your periodic table to make sure. Okay, and this would just be Ba is barium. It is not a transition metal, so we don't need a Roman numeral. So it would be barium nitrate. Okay, real quick example. So that's barium nitrate. So if I had Ba, okay, with 3, N2, this would be barium nitride. So just be careful. So ide is only for monoatomic. So if it's just nitrogen by itself, okay, that's a monatomic. So mono means 1. Okay, so that would be nitride. Nitrate, nitrite, that's when you're dealing with polyatomic. So just kind of watch out for that. Okay, so let's do just a couple more examples and then we'll be done. Okay, so now I'm going to give you a name. So I'm going to say mercury 1 nitrate. Okay, so mercury 1 nitrate. So nitrate, if you look on your list, is NO3 with a -1 charge. So I did my anion first. Mercury is going to be Hg. And that I told me it's a transition metal, so that tells me this mercury is going to have a charge of +1. Okay, I have a +1, I have a -1, so this is already balanced. So this would just be HgNO3. That's it. It's already balanced. Okay, let's try another one. So iron 2 phosphite. So I'm going to do iron 2 phosphite. So phosphite. So we need to look up, just to make sure everyone's on the same list. Phosphite's right here, so which is PO3 with a -3 charge. So PO3 with a -3 charge. Oops, my name went somewhere. So iron 2 phosphite. Okay, and we determined it was PO3 with a -3 charge. Okay, iron 2. So iron is Fe. That 2 tells me it's a charge of iron, so which is +2. So this is where you can do the crisscross. So that's 3 goes here, that 2 goes here. So that means I need 3 irons. So Fe3. And I need 2 phosphites. So I'm going to put phosphites in parentheses. So PO3 is in parentheses. I'm not going to touch it. And I need 2 of them, so I'm going to put a 2 on the outside of it. Okay, so I know that kind of color didn't really work out. So that's PO3 with a 2 on the outside of the parentheses. So that's it. That's balanced. So hopefully that kind of helped out with that a little bit. So you can rewind it, go back through that again, and let us know if you have any questions.